We've explored algorithms, tuned models, and built ensembles. Now it's time to bring it all together. Welcome to day 29 and 30 of the 30 Days of Machine Learning series. In this final video, we'll build a complete project with the diabetes dataset using everything we've learned, from pre-processing to classification and saving the best model. If you're new here, the full series playlist is linked. Go check it out. And don't forget to subscribe. More ML and Gen AI content is coming soon. Let's wrap up the series with a solid project. We're starting off by importing all the tools we'll need for our project. Pandas and NumPy help us handle and manipulate the data, while Matplotlib and Seaborn are perfect for visualizing patterns and distributions. Joblib will let us save our final model for future use. From Scikit-Learn, we're bringing in a full toolkit, everything from model building and pre-processing to evaluation. We've got multiple classifiers like logistic regression, decision trees, random forests, and gradient boosting, along with metrics to measure how well our models perform. This setup gets us ready for a complete end-to-end ML pipeline. We start by loading the diabetes dataset using RED-CSV. With dot shape, we check how many rows and columns we're working with. Dot head gives a sneak peek at the first few entries, while dot info helps us understand data types and missing values. Here, we're converting the gender column into numeric values. We replace female with 0, male with 1, and other with -1. This helps our machine learning models understand and work with the data more effectively. First, we check how many unique categories are in the smoking history column using value counts. Then, we convert each category into a number, like no info to 0, never to 1, and so on. This label encoding helps models interpret the smoking data in a meaningful numeric format. We preview the updated data and check value distributions in each column to spot imbalances or unusual patterns. We plot a heat map to visualize how features relate to each other. High correlations help us understand patterns and possible feature importance. We first check for missing values using .isnl.sum. Then we visualize how age is distributed across diabetic and non-diabetic individuals using a histogram. We use a box plot to compare BMI across genders, separated by diabetes status. This helps us spot trends or outliers in BMI based on gender and health. We create a count plot to see how smoking history relates to diabetes. The hue shows diabetic versus non-diabetic counts for each smoking category. We plot KDE curves for key numeric features like age, BMI, HbA1c, and glucose levels. This shows how their distributions differ between diabetic and non-diabetic groups. We use a box plot to compare blood glucose levels across different smoking history groups, split by diabetes status. It reveals patterns and outliers clearly. We plot a pie chart to visualize the class distribution of diabetes in the dataset. It helps us understand if the data is balanced or skewed. We split the data into features X and target Y, then use train test, split to create training and testing sets, keeping class balance with stratify equals Y. We scale the feature data using standard scalar to normalize values. This helps models train better by keeping all features on a similar scale. This function makes model evaluation super efficient. We pass in the model and data. Then it trains the model, makes predictions, and prints out all key metrics: accuracy, precision, recall, F1 score, and the confusion matrix. It also generates a classification report for deeper insights. If the model supports probability predictions, it calculates the AUC-ROC score and plots the ROC curve, which helps us visualize how well the model separates classes. This reusable function lets us compare different models easily and consistently, without rewriting code every time we want to evaluate a new one. We define a dictionary of classification models to test: logistic regression, decision tree, random forest, and gradient boosting. This setup makes it easy to loop through and evaluate each model using our evaluate our model function, helping us compare performance and choose the best one for our task. We evaluate all models in a loop and plot their ROC curves on one graph for easy comparison. The diagonal line shows random guessing. Models above it perform better. This visual helps us quickly spot which model gives the best trade-off between true positives and false positives. We use GridSearchCV to fine-tune the random forest model by testing different combinations of n estimators and max depth. It runs cross-validation to find the best performing hyperparameters and prints out the top configuration along with its accuracy score. We save the best random forest model and the scalar using joblib, so we can reuse them later without retraining. This is the final step in making our ML project production ready. And that wraps up our end-to-end machine learning project using the diabetes dataset. We applied everything we've learned, from pre-processing and visualization to training, tuning, evaluating, and finally saving our best model. If you made it this far in the 30 days of machine learning, congrats! You've built a strong foundation in ML, and you're ready for real-world projects. But we're not stopping here. Stay tuned for the next series on generative AI. It's going to be more interactive, more hands-on, and even more fun. Make sure you subscribe so you don't miss it. Thanks for watching. See you in the next series.